makes the discussion richer. Okay, so first of all, what we're going to do, you guys, is we're going to go over the antibiotics. We're going to classify them and describe the target and which functions they knock out. So all of that information will be fair game on the quiz, and it's also information that could be asked on the final exam too, okay? So we'll start first with penicillin. Penicillin, you guys remember, is the first antibiotic discovered by Sir Alexander Fleming, made by the fungus Penicillium. And let me quiz you guys, okay? And don't worry if you don't know. Guessing is good. So what is the target of a beta-lactam like penicillin? What structure does it bind to? Or, yeah, what does it bind to in a bacterium?
Peptidoglycan.
Okay, now, and that's close. It's close. But do you guys remember we said that penicillin and other beta-lactams, they're irreversible competitive inhibitors of which enzyme?
Beta-lactamase.
Okay, and that was a good guess. It was a good guess, and it's so good you guys are guessing. What?
Guessing.
Okay, and you're getting so close.
A bacterial transpeptide.
That's it. Remember, you guys? Okay, so beta-lactams, such as penicillin, they're irreversible competitive inhibitors of bacterial transpeptidase. So they bind, they stop the function of the transpeptidase. So what doesn't happen? So what? That is right. Remember, if the bacterial transpeptidase can't function, you aren't going to get those peptide phospholylates in your peptidoglycan, and as a result, the peptidoglycan is going to be weak. So if the bacterium is growing in a hypoosmotic environment, what will happen to the bacterium? Osmotic lysis, dynamite, you guys. Excellent. Okay, so penicillin, the first antibiotic discovered, our grandfather beta-lactam. Now, one of the problems with penicillin is it's a large hydrophilic molecule. So to cross the hydrophobic outer membrane of gram-negative bacteria, it has to pass through those porins, those protein channels in the outer membrane. And it turns out penicillin is too large, it has the wrong shape to pass through the outer membrane porins of most gram-negatives. So usually we say penicillin is relatively narrow spectrum. We use it primarily for gram-positive bacteria. There's always exceptions to the rule, you guys. So, for example, Neisseria gonorrhea, which is a gram-negative bacterium, penicillin can cross the outer membrane. So you could use penicillin in the old days to treat gonorrhea. But just in general, we say that penicillin, you just presume if you got a gram-negative bacterium, usually you don't choose penicillin right off the bat. Okay? Can't cross the outer membrane of most gram-negatives. So what they did was, because people wanted to be able to use a penicillin-like antibiotic against gram-negatives, they chemically modified penicillin to make a semi-synthetic beta-lactam, semi-synthetic penicillin. And one of the most famous ones is the second beta-lactam you guys are working with, ampicillin. Ampicillin's been chemically modified, so now it can cross the outer membrane. It can cross through the porins of many gram-negatives. So we say that ampicillin has broader spectrum of activity against both gram-negatives and gram-positives when compared to penicillin. So again, ampicillin, broader spectrum, can be used against both gram-negative and gram-positive bacteria. Okay, so those are our two beta-lactams. Both of these beta-lactams, you guys, this is important, are sensitive to destruction or hydrolysis by beta-lactamases. Okay, so both of these antibiotics, if they were used to treat a bacterium that makes beta-lactamase, they would be destroyed. That was one reason why methicillin, another beta-lactam, was developed. Methicillin is resistant to beta-lactamases. And so then we went ape using methicillin, and then we selected for methicillin-resistant Staph aureus. So you guys know that story. Okay. Okay, now we're going to leave our beta-lactams, and we're going to move to another group of antibiotics that target the 70S ribosome of bacteria, prokaryotes, right? What kind of ribosomes do we have in our cytoplasm?
80S.
80S, right? So these antibiotics won't bind to our cytoplasmic ribosomes. Okay, so let's back up here. So if we expose a bacterium to erythromycin or clindamycin or tetracycline, which function will be stopped?
Protein synthesis.
Exactly, protein synthesis. What's a fancy term for protein synthesis? Translation. And the reason I bring that up, you guys, is I've seen that on exams, sometimes if I use the term translation instead of protein synthesis, people get confused. And so remember, protein synthesis is translation, right? So we could use either term, okay? So we could say that erythromycin, clindamycin, tetracycline, they bind to the bacterial 70S ribosome and stop protein synthesis or stop translation, right? They won't bind to our 80S ribosome, so that's why these drugs aren't toxic for our cells. Erythromycin and clindamycin are structurally related to one another, and both of them also are primarily used for gram-positives. And it's going to sound really similar, the story here. Erythromycin can't cross the outer membrane of most gram, I'm sorry guys. The clindamycin can't cross the outer membrane of most gram-negative bacteria, so it's primarily used for gram-positives. It's often used for oral infections where you might predict you might have some staphylococcus, streptococcus. But really important, you guys, and I'll try to put a star here by it. Use of clindamycin is a risk factor for later developing Clostridium difficile infections in the intestines, the C. diff infections, right? Come on, this is exciting. We're talking about yummy bacterial infections. I'm teasing you. Okay. So let me ask you guys, let's say that you are hospitalized or, when you get old, if you're in a nursing home and say you develop bacterial infection, so your doctor wants to put you, doctor thinks it's gram-positive bacterium, so he puts you on clindamycin. Okay, so it wipes out all your good bacteria, right? All your protective bacteria. Now, if you have some Clostridium difficile endospores in your intestines, why Clostridium, the genus Clostridium, they're gram-positives, right? So why doesn't the clindamycin kill the Clostridium difficile endospores in your intestines? What do we know about endospores? They laugh at antibiotics, right? Because they're those tough resistant structures. So endospores are not destroyed by antibiotics at all, right? So if your put on clindamycin kills your good competitive bacteria in your intestine, the Clostridium difficile endospores are not going to be killed. Eventually you take your you come off that clindamycin, so now those endospores germinate, and there's nobody to compete with them, right? So they grow to really high numbers, they can cause diarrhea, they can produce toxins that can even perforate your intestine, and that, of course, can be life-threatening, right? So be careful with clindamycin. Yeah, just remember that you might have C. diff infections later on. Okay. The erythromycin, it's similar to, the erythromycin, if you read in the pharmacology books, they say that many of the Enterobacteriaceae, that big family to which E. coli belongs, many of them carry resistance plasmids that have erythromycin resistance genes. And probably, too, there is problems with the erythromycin crossing the outer membrane of gram-negative. So, again, usually erythromycin you're only going to use on gram-positives. Okay. And then the tetracycline is definitely broad spectrum. This is an antibiotic which historically has been added to livestock feed and poultry feed to increase weight gain and milk and meat and egg production. So we're going to see in our data that there's been a lot of selection for tetracycline resistant bacteria. Okay, so that's something I wish we could stop. I wish we could stop using so much antibiotic in our livestock and poultry feed. Okay, the gentamicin, some of you have gentamicin. Gentamicin, as we said, belongs to this big family of aminoglycosides. Their target is the same. They're going to target that 70S ribosome. Aminoglycosides, you have to be careful, you guys, because aminoglycosides can cause kidney damage. They can be nephrotoxic. And in some people, they cause damage to the auditory nerve, right? So you got to be careful. There's kind of a big gun there. Trimethoprim and sulfamethoxazole inhibit enzymes involved in bacterial folic acid synthesis. Folic acid is a coenzyme for nucleic acid synthesis. So if you inhibit the ability of the bacteria to make folic acid, they can't make DNA, so they can't copy their chromosomes, they can't replicate. And also they wouldn't be able to make RNA, so they can't carry out transcription, and thus you're going to knock down protein synthesis as well. Okay? So the beauty of this antibiotic combination, often called Bactrim, is it uses two of the inhibitors of folic acid synthesis. these inhibit two enzymes in the folic acid metabolic pathway, so they're often referred to, trimethoprim and sulfamethoxazole are often referred to as sequential inhibitors of folic acid synthesis. Okay, so let's take a look at our data, and let's first talk about our microbes that we use. So you guys help me out here. Is E. coli gram-negative, gram-positive, or acid-fast? Gram-negative, that's important to know. It's got that protective hydrophobic outer membrane, okay? Pseudomonas fluorescens. Pseudomonas is a very serious opportunistic pathogen in hospitals. It's often found, you guys, this is crazy, growing in soap containers and in disinfectant bottles in hospitals. That is crazy, right? Okay, so what do you think, gram-negative or gram-positive? Okay, that was a good guess. Try another guess.
Negative.
Acid.
Negative.
Oh, that's a good guess too. Try another guess. You guys are so good. Okay, it's gram-negative too. Okay, so it's going to have, unfortunately, that outer membrane. Good for you guys. It's great when you guess. Okay, Staphylococcus epidermidis.
Positive.
Gram-positive, great, you guys. And unfortunately, we don't have an acid-fast bacterium because we're going to describe how probably those would be the ultimate resistant bacteria. Okay, so let's take a look at our E. coli and see what kind of results we get. Okay, so we know penicillin can't cross the outer membrane of most gram-negatives. So would you predict E. coli might be naturally resistant to penicillin?
No.
Yeah, because it's got that protective outer membrane, right? And what did your results reveal? It supports that hypothesis, right? The penicillin can't cross the outer membrane. So, we see here penicillin is not a good choice to try to treat an E. coli infection. Now we know ampicillin has been chemically modified so it can cross the outer membrane of gram-negative. So we might hope ampicillin maybe could kill the E. coli, and what did we find out? Yes, it did, yeah. So there you go. That's kind of nice. Our data reflects the ampicillin is broader spectrum and can kill gram-negatives at therapeutic levels, right? That's dynamite, you guys. Okay, erythromycin. Do you guys remember we said erythromycin is usually used on gram-positives? And it's because there's either issues with erythromycin crossing the outer membrane of gram-negatives, or they often have those R plasmids. So we might have predicted the E. coli would be what to erythromycin? Predict resistance, right? And what did our data show? Oh, kind of intermediate here. Okay, that's all right. Intermediate, you guys. It's like people say, what does intermediate mean? Well, it's kind of what it suggests. It's somewhat inhibiting the bacteria, right? Not 100%. So it's a clinical decision whether to use an antibiotic that has intermediate activity against the bacterium. The most important thing for you to ask is, what is the status of your patient's immune system? If they're young and robust, have a dynamite immune system like you guys, and say that there's a relatively non-toxic antibiotic, and you're getting intermediate activity against the bacterium, maybe you'd go with that one, right? But if you have a patient that's severely immunocompromised, maybe they're HIV/AIDS patients, maybe they have cancer, you would want to go for an antibiotic that has high activity against the bacterium. You wouldn't want to use an antibiotic that has intermediate activity, right? Okay, and just to kind of add to this, you guys, in yesterday's lab, they were getting actual small zones of inhibition, so they're coming up with resistance with the E. coli and the erythromycin, which is what we predict, that the erythromycin usually isn't very active against gram-negatives. And usually the prediction is, if you have erythromycin resistance, you're going to have clindamycin resistance. And again, clindamycin has a hard time crossing outer membranes gram-negative, so our data supports that. The broad-spectrum tetracycline that gets added to a lot of animal feeds. The good news is, we've got a little bit of mixed results here, you guys. And what I did yesterday, I just went with the predominant finding. So you guys, we've got, if we include yesterday, we have 3 sensitive and 1 resistant. If you guys are okay, we'll go with sensitive on the tetracycline here, okay? So reflecting its broad spectrum activity. And then in our trimethoprim, wow, this is so interesting, you guys. So we've got, let me just ask, did anybody, did any other group that didn't post their findings up here have the TMP, just the trimethoprim? Because that's really interesting results we have there. Just trying to, because we're kind of a split decision here, just trying to get a little bit more data. Anybody? Okay, so we're gonna have to go question mark there. When trimethoprim is combined with the sulfamethoxazole, so we're getting two-step inhibition of two different enzymes, then we are getting, we are seeing therapeutic level of killing of our E. coli with the combination trimethoprim sulfamethoxazole. Okay, now what do you guys notice about our Pseudomonas? Oh my goodness.
Oh my God.
And you guys, this, oh, except you guys got tetracycline. Oh, that's cool. Well, that's good. Okay, yesterday they got resistance there, so we'll put an SR. Okay, and we got resistance there and resistance there. Okay, and that is scary, isn't it? And I wanted to share with you, that's what the Pseudomonas that caused those hospital outbreaks, the same pattern. Remember, Pseudomonas is gram-negative. Antibiotics, water-soluble antibiotics, would have to pass through the outer membrane porins. Well, it turns out that a lot of Pseudomonas, and many antibiotics cannot fit through their porins, right? And that's reflected in this incredible multi-antibiotic resistance here. So this is very real world, you guys, and this is also why I want you to wash your hands before you go, because you don't want to take the Pseudomonas home with you, right? Yeah.
We got gentamicin and that was very sensitive.
Oh, you got, okay, thank you. You guys had gentamicin, and it was sensitive?
Yes.
Oh, dynamite, you guys. Okay, that is good to know. That is good to know. So the group that had the aminoglycoside gentamicin, it did kill the Pseudomonas, and that is good to know. The only thing you want to remember with gentamicin is kidney damage. They're nephrotoxic, and they kind of cause auditory nerve damage. So if you had a patient with kidney disease, you'd have to be really careful with the gentamicin. But that's good to know. We got one that will kill it. Yeah, Octavia.
So since the majority of us are going to be working, excuse me, a hospital setting, what precautions can we take as far as the hand washing, since it can be in the soap dispensers? And
Oh, right, yeah. Yeah, that's good. Well, the good thing, okay, so the one thing with soap, the idea is it's surfactant, you're trying to wash things off. So if you rinse your hands really well, in theory, you know, you should be getting most of the Pseudomonas off. Now, see, I'm like, what do they call it when you build up something and make it more dramatic? You know, obviously, we aren't seeing ongoing Pseudomonas hospital outbreaks from the soap dispensers, right? But it's just something I wanted to remind you guys. If you are in a medical setting and you do have an outbreak of Pseudomonas in your healthcare facility, don't forget to, you know, to culture the soap dispensers and the disinfectant, right? And sometimes it might be a matter that you just need to change the dispenser, buy new ones, or, you know, go in there with your 1 to 10 diluted bleach and really clean the daylights out of them. Pseudomonas are great at making biofilms, right? So they're forming biofilms in there, and that's one way that they can get away with colonizing there, right? Yeah. But you would probably have evidence of an outbreak of Pseudomonas in your hospital or clinic, and then just remember to culture those. Okay. Yeah, okay, so do remember, you guys, Pseudomonas nasty, multiple resistance to antibiotics, and probably a lot of it is that wonderful outer membrane, yeah? Okay, and then our Staphylococcus epidermidis can act as an opportunistic pathogen, but it's also kind of our stand-in for Staphylococcus aureus. And this really startled me, you guys. Look at this. Oh my goodness. Okay, so resistant to pen, resistant to ampicillin. It looks to me like our stock culture is making which enzyme? Which enzyme can destroy penicillin and ampicillin? Beta-lactamase, right? And had this been a Staph aureus, we would have said, well, of course, you know, like 99% of Staph aureus carry the beta-lactamase gene. But for our stock cultures, we should not be working with Staph epi carrying a beta-lactamase gene, because we know horizontal gene transfer, right? We don't want this stock culture transferring that gene to some of your bacteria. So this one, I think the stock culture needs to be autoclaved, right? But again, you guys, just be careful. Wash your hands, spray down your benches. So this really looks like our Staph epi strain carries a beta-lactamase gene like most Staphylococcus aureus strains do, right? Just hydrolyzing the daylights out of those beta-lactams. So the good news is, you know, as instructors, we were relieved to see, well, at least the Staph epi strain is sensitive to erythromycin and clindamycin, the big macrolides, okay? But what about this, you guys? We've got tetracycline resistance. So we've got a multi-antibiotic resistant strain of Staph epi. That's starting to look like an R plasmid, don't you think? Seeing this multiple antibiotic resistance. So it's kind of interesting for us to see if our Staph epi strain is carrying an antibiotic resistance plasmid. Okay, and then so we're getting mixed results on the trimethoprim again, you guys, but with the combination, trimethoprim, sulfamethoxazole, you know, luckily this guy is inhibited by therapeutic levels there. Okay, so wow, that was a big surprise. Wow, okay. So let's just do a checklist, you guys, to make sure we've hit all the key points. And again, this will help not only with the quiz, but it's going to help with the final exam. So we want to make sure that we're aware of how cell wall structure of bacteria may influence the resistance to antibiotics. Gram-positives, remember, thick layer of peptidoglycan, very hydrophilic, no protection against hydrophilic antibiotics or disinfectants or antiseptics. The gram-negatives, thin layer of peptidoglycan, but that incredible hydrophobic outer membrane provides a lot of protection. And the kings of chemical resistance based on cell wall structure would be who? Acid-fast bacteria, right? And remember, they have that really thick, waxy, very hydrophobic, mycolic acid-rich cell wall. So the acid-fast bacteria are the kings of resistance to bacteria based on cell wall structure. We want to remember that bacterial endospores made by the genus Bacillus, such as Bacillus anthracis, that causes anthrax. Endospores made by the genus Clostridium, so Clostridium difficile, Clostridium tetani, Clostridium botulinum. The endospores will be totally resistant to antibiotics, right? So we just need to remember that. We discussed the activity of penicillin and ampicillin. We said that both of them are hydrolyzed by beta-lactamases, as demonstrated by our lovely Staph epi here. We talked about the rather narrow spectrum use of erythromycin and clindamycin for gram-positives. And, oh, yes! So, I'll hit this last topic, you guys. And we do want to be aware that a big step that the U.S. could make is to reduce the use of antibiotics in livestock feed and poultry feed. And that will definitely reduce selection for antibiotic-resistant bacteria. And then the final topic, you guys, is mechanisms of antibiotic resistance. Shireen did this great poster back here. So that's a lovely reference. But let's just list some of the mechanisms of antibiotic resistance just to review them. So we've already described how cell wall structure can provide protection against antibiotics. We want to be aware that formation of endospores, the endospores will be resistant to antibiotics. But in addition, bacteria can carry genes for antibiotic resistance that encode proteins that make what are called efflux pumps. These are little pumps that as soon as the antibiotic crosses into the cytoplasm, the pumps in the cytoplasmic membrane pump the antibiotic right out again. Antibiotic resistance, we can have enzymes that hydrolyze the antibiotics, like beta-lactamases. We could have enzymes that chemically modify the antibiotic, for example, adding a methyl group so that the antibiotic can no longer bind to its target. That often happens with erythromycin resistance. We could have the bacterium undergo mutation so that the target is a different shape. We have a mutant target, and then the antibiotic can no longer bind to the target. That's what's happened with methicillin-resistant Staph aureus. They make a mutant transpeptidase so that the beta-lactams can't bind to that transpeptidase anymore. Isn't that sneaky? I mean, they're just brilliant. They're brilliant. Another important thing for us to remember, you guys, remember how we said earlier in the course that human infections with bacteria probably very often involve biofilms. We want to remember bacteria and biofilms, usually they're in stationary phase of growth and they're naturally resistant when they're metabolically inactive. And also in a thick biofilm, The antibiotics have trouble diffusing through the layers of the biofilm, so the bacteria in the lower layers are going to be naturally protected from high levels of the antibiotic. Okay, so biofilms are a great way for bacteria to protect themselves against antibiotics. Okay, all right. And so, Sarah, you have questions? Sorry. Okay, I know. So, I think that does it, you guys. So, I know that's a lot, but again, hopefully that discussion will help you not only for the quiz on Tuesday, but will also help you with, quite a few questions on the final exams. Okay? All right, folks. So, now, those of you that want to check out today, you don't have